This is our square root perfect square homework solutions. And the first question is to determine the value of the square root of 4. Now, in order to do that, we're going to have knowledge of this list here. So let's look at this list in more detail. We can only evaluate a radical where what's under the radical, like in this problem here, we see the value 4 under our radical. We can only evaluate what we call perfect squares. Now, if I take any base, and I'll color my bases here in orange, any base, the value 1, 2, 3, 4, or 5, and I raise that base to the second power, what we see is something called perfect squares. So 1 squared is a perfect square, 2 squared is a perfect square, 3 squared is a perfect square, 4 squared is a perfect square, and 5 squared is a perfect square. Those values are 1, 4, 9, 16, and 25. So anything that I raise to the second power, any base that I raise to the second power, is known as here's a base to the second power, it's known as a perfect square. Now, in order to go in reverse, to take the square root of a perfect square, we simply answer this question. What was the base that we squared in order to get the perfect square? So all the answers in orange is here on the left side. 1, 2, 3, 4, 5. These are answers for various square roots of perfect squares. You can only answer these questions if you have knowledge of this table. So your responsibility is to knowing this table. Know how to produce perfect squares by taking things to the second power so that you know how to undo them and take the square root of these perfect squares. These are the only square roots that we can evaluate perfectly, I guess, or in some sense, very easily. So, with that said, and I'll keep this in orange, that the square root of 4 is the value 2 here. And the reason is simple, because the square root of 4, first of all, we know 4 is a perfect square. It was 2 to the second power. The base that was squared here is right in orange. It's the value 2. And this is how we answer the question. It's simply having knowledge of this table and these relationships. Number 3. We have the square root of 25. Now, if I go back and look at my table, and maybe it's a good idea to get a fresh table. If we notice, 25 again here is a perfect square. We are taking the square root of perfect squares. Now, what was the base that was raised to the second power in order to get 25? Well, 5 squared, which meant my base is really what? 5. The square root of 25 is 5. We are done. Number 5, the square root of 100. Using our table. we notice that the number 100 is a perfect square. The square root of 100 is determining the base that was raised to the second power. In this case, the base was 10. Our answer is the square root of 100 is the value 10. Number 7. The square root of 64. Notice that 64 is a perfect square. It's on our perfect square list. We now have to find the base that was raised to the second power to obtain 64. The value is 8. So the square root of 64 is actually 8 because 8 squared is 64. The base was 8. Number 9. The square root of 16. Let's notice that 16 is a perfect square. It's over here. It's on our list. This is the list of perfect squares. Now the base that was raised to the second power is the value 4. So that the square root of 16 is 4. Number 11. We have minus square root of 4. Now let's notate something very important here. That there's actually two statements going on here. This negative 1 is really negative 1 times negative 4. Sorry, negative 1 times the square root of 4. Now we know that the square root of 4, or I should start off by saying simply that my number 4 is a perfect square. Because the base that was raised to the second power to get a 4 is actually 2. So this becomes negative 1 times 2, which will be negative 2. So there's two things going on. We're going to multiply the square root of 4 with the value negative 1 to simply obtain negative 2. Number 13. Negative square root of 25. This is negative 1 times the square root of 25. Notice 25 is a perfect square because 5 to the second power is 25. So the base here is 5. So the square root of 25 here, we can replace this with the value 5. We get negative 1 times 5, which is negative 5. Number 15. Negative square root of 100. Negative 1 times square root of 100. And we already know that 100 is a perfect square because 10 to the second power is 100, so that the base that was used to get 100 is the value 10. The square root of 100 is 10, so this is negative 1 times 10, or negative 10. Number 17, minus square root of 64. Negative 1 times square root of 64. And we know 64 is a perfect square. And we know this because 8 to the second power is 64. That the base that was used here is 8. So that my radical then becomes simply the value 8, and now I have negative 1 times 8, which is negative 8. Number 19, the square root of x squared. Now, let's take a look at this. If we look at the list here, we notice that we don't only have values here on this list. We have these variables, in that x squared is a perfect square because it's on our perfect square list. Now we have to answer what base was used here to obtain x squared. What was raised to the second power? And that was simply x. So that the square root of x is really, or I should say the square root of the perfect square, x squared, is really x. Number 21. Square root of x to the fourth. X to the fourth is a perfect square. Now let's go into some detail here. If we look at our list again, we notice here on this list of perfect squares that x to the fourth here is a perfect square. Now we have to find the base now that was raised to the second power to get the 64. If we look at this, we find the value to be x squared. Here, here. So that our final answer here will be simply x squared. That was the base that was raised to the second power to get x squared. Now, I want to give you a note. We can also do this in another way. We know the base x squared raised to the second power by properties of exponents. We can take our 2 times our 2, and that gave us the 4. This is why we have a perfect square. So I'll know that simply taking x squared and raising that to the second power here, well, this is my base. So that the square root of x to the fourth power is x squared. This is one way to look at this. There's a shortcut though. Let's recall that the radical can be expressed as a power, meaning if I take anything here, it doesn't matter what it is. If I take this shape, maybe we shouldn't use that shape. Let's use a happy face. The square root of a happy face can be written as the happy face to the 1/2 power. I can describe my base here with a fractional power, where my index for the square root is here as a 2. This is what we call an index value. If you don't see a value, it's always, by default, 2. And the numerator for your power is always 1 here. So this is going to be important for us for some of these problems, because I can now describe the square root of x to the fourth as x to the fourth, my base, to a 1/2 power. If you remember from beginning algebra, that 4 times 1/2, or I should say, if you have a base raised to a power to another power, here's what we're focusing on. My base raised to the fourth power raised to the 1/2 power. I simply multiply my powers. Now 4 times 1/2 is the value 2. Final answer is x squared. We're going to be using this approach here to answer some of our questions on our homework. (23) The square root of x to the 6. Let's remember that we can write this as x to the 6 raised to the 1/2 power. Again, if there's no index, it's understood to be a 2. So that I always write the 2 here as a denominator for this base of x to the 6th power. And 1 is always the numerator. At this point, x to the 6 raised to the 1/2 by properties of exponents. Let's look at this in detail. 6 times 1/2. I multiply 6 with the 1/2 power. So I get 6 times 1/2, which gives me 3. This is x cubed. So that the square root of x to the 6 is x cubed. Now if I go back to my sheet, and I'm looking at x to the 6, let's notice x to the 6 is a perfect square, and the base that was used to get x to the 6 turns out to be x to the 3rd power. That's the same answer. 25. The square root of c to the 22nd power. We could simply write this as c to the 22nd power raised to the, well, let's double check. The index is 2, so this will be raised to the 1/2 power. And then any base, c raised to a power to another power, requires us to simply multiply the powers. So this is 22 times 1/2. we'll end up with c to the 22 divided by 1/2. Because when I multiply a whole number with a fraction, and the fraction has a numerator of a 1, 22 times 1 is 22. So this becomes 22 divided by 2, or 11. Now I'm going to give you another note, because this gives you an even shorter way of answering the question. If I notice they don't give me an index value, by default, the index is 2. As a shortcut, even further, I can write this as the following. C to the 22 divided by the index of 2. So I can always divide my power by simply the index, and this makes everything a lot easier. Go back up here. The justification is what you see here, that when I take these numerators here, 22 times 1, I always get 22. So I might as well always simply divide my power, if I can, by 2, since that's my index here. An even shorter way. Final answer is going to be the base c raised to the 11th power. 22 divided by 2. An even better way. 27. Square root of 4x squared. Now we talked about in class what I call the product rule for square roots. Here's the product rule. The square root of a happy face times a heart is equal to the square root of a happy face times the square root of the heart. Notice what you guys see here. Under the radical, you have a happy face multiplied to a heart. That's under a single radical. And your operation's multiplication. Well, that could be written as the square root of the happy face times the square root of your heart. We call this the product rule because what's happening here is a product. This is what we're going to use. So when I have the square root of 4x squared, I can write this as the square root of 4 times the square root of x squared. I know the square root of 4 is 2, and I know the square root of x squared is x. My final answer really is 2x. Let's note that 2x raised to the second power by properties of exponents was 2 squared x squared, which is 4x squared. Meaning 4x squared is a perfect square, and the base that was used to raise to the second power was a 2x. What that always means is that the square root of that perfect square is equal to that base of 2x. That's the same answer we got above. Number 29. The square root of 25y to the 4th power. By the product rule, square root of 25 times the square root of y to the 4th power. The square root of 25 is 5. The square root of y to the 4th power, let's remember, they didn't give us an index. By default, it's 2. So we're going to write this as the following. Y to the 4th power, that's my base, divided by the 2. That's the index. An even shorter way. index, index. We get 5y squared. We are done. (31) The square root of 36 x squared y to the fourth. What we've seen in class was the product rule can be generalized to any number of terms. Meaning, if we identify that we have 36 as a perfect squared, x squared as a perfect squared, y to the fourth as a perfect squared, our operations must be multiplication and multiplication. We can simply simplify each perfect square separately. Square root of 36, square root of x squared, and the square root of y to the fourth. What we find is we get 6xy squared. And you're done. Don't forget, this is really multiplication here between my terms because there's a blank space. Point being, this is 6xy squared. Number 33. Square root of 4 x to the 8th, y to the 12th, and z to the second power. It's yet again continuation of the concept of we can generalize the product rule. So we have the square root of 4 times the square root of x to the 8th, the square root of y to the 12th, times the square root of z squared. All perfect squares. 4 x to the 8th, x to the 12th, z squared. And again, notice the operation here between all of them has to be multiplication. Let's simplify. The square root of 4 is 2. The square root of x to the 8th is x to the 8th. Let's divide by the index of a 2 times y to the 12th. I'm going to divide by the index of my 2 times z to the second power. We're going to divide by our index of 2. This is going to simplify to 2x to the 4th, y to the 6th, z to the first power, which is really z. We're done. (35) The square root of a quotient. Similarly, we have the quotient rule for radicals, and that was the following. The square root of a happy face divided by a heart can be described as, separately, the square root of your happy face over your heart equals the square root of happy face divided by square root of heart. The square root of a quotient is quotient of square roots. Similar to the product rule, if we go back. Okay. You have a numerator here. Numerator. You have a denominator. Denominator. Notice the operation this time is division. What this means is the square root of 1 divided by the square root of 4. The square root of 1 is 1 and the square root of 4 is 2. We are done. Number 37. The square root of 4 divided by 9. By the quotient rule, the square root of a quotient is quotient of square roots. The square root of 4 is 2. The square root of 9 is 3. We're done. Number 39. The square root of a quotient. Let's do it over here. The square root of a quotient is quotient of square roots. The square root of x squared is x, and the square root of 25 is 5. You are done.